Differential equations used in all sorts of areas, see, physical, biological, social sciences, it's everywhere. You can come up with mathematical relationships using derivatives. How does something change with respect to other? And we create these equations involving derivatives, known as differential equations. So here's an example of one which you may not recognize it written like this, but it's something that is actually very familiar to you. It is, of course, Newton's second law of motion, force equals mass times acceleration. It's just written differently. Instead of acceleration, we've written it as the second derivative, and force, we've said, is some function of x, but that is what that is. This one here you may not recognize, but it is a differential equation. This one controls damped oscillation. So something like a shock absorber. So it defines how far up and down the car might bounce because of the shock absorber. This one here is quite an interesting little equation. It's what's known as the logistic equation, also known as the Lotka-Volterra equation, also known as the predator-prey equation. All sorts of names it has. All of these things are called differential equations. Now the order of the equation is basically whatever the highest order of the derivative is. So the very first one there is a second order differential equation. The second one is also a second order differential equation, whereas the last one is just a first order differential equation. Now unfortunately, well I say unfortunately because it's fun looking at higher order ones, this course is pretty much limited to first order differential equations. That's not to say we can't look at other ones and have some fun. So how do we solve these things? Well, basically it's integration, which is something we've been doing for a while now. Now, we have things called general solutions. So the general solution is a family of curves, all the possible answers. Basically, it's the indefinite integral. So the indefinite integral, you have plus a constant, so the curve could shift up, and you have it in all different positions. So you get a family of curves. A particular solution is one that solves an initial value problem, and that's like the definite integral. So when we go and integrate, we've been given some initial conditions we can sub in and say, oh well, of this family of curves, which particular one are we interested in? So that would be the particular solution. Let's have a look at this one. X times the y dx plus y is equal to 0. Again, it's something we can easily handle, and I'll do it by what we call separation of variables. I'll just move the y over the other side and rearrange it, and I can get that dy over y is equal to dx over x, but then just whack in a couple of integral signs on both sides. Because at the end of the day, it's an equation. Whatever you do to one side of the equation, you must do to the other. So if I integrate one side, I must integrate the other. So when we integrate both sides, on the left-hand side we get minus the log of y, right-hand side log of x. Somewhere there's a constant. It really doesn't matter which side I put it on, so I'll put it on the right-hand side. I can rewrite that to get the log of xy is equal to negative a constant, but negative a constant is still a constant, so what does it really matter? If I exponentialize both sides, I get e to the minus k, but again, that's just a constant number, so I'll call it a constant number, and y equals c over k, and you'll notice I got rid of the absolute value signs. And why? Well, because that constant number could be negative or positive anyway. There is the general solution y equals c over x in different possible values for c. If we had the initial value problem that y1 is 1, so when we substitute x equals 1 in, we get 1, then the constant would be 1. So the particular solution to this problem would be the one in black there, y equals 1 on x, would be the particular one we were looking for. So what's a linear differential equation? Linear basically means that. And you might be looking at that and thinking, well, how's that a straight line? No, they're not talking about a straight line. Right? Linear just means we've got all these derivatives and they're multiplied by some function of x. Each one of them is multiplied by some function of x. Notice you've even got the, well, for want of a better word, the north derivative. Right? See how you got the nth derivative, then the n minus 1th derivative, first derivative, and then you just have y itself, which, I don't know, it's at the north derivative. You could think of it like that, I suppose. So first order linear differential equations, that's pretty much what we look at First order linear differential equations. Something in that format. The derivative plus some function of x times y is equal to some other function of x. Now, if function x is equal to 0, then it's just an indefinite integral. We can rearrange that, separate the variables and do it as normal. If it doesn't equal 0, it becomes a lot more interesting. And we have to multiply by what's called an integrating factor. And that integrating factor has this formula. E to the integral of gx dx. So whatever that function is in front of y, we'll go e to the power of the integral of that, multiply everything by it, and we should then be able to get something we can integrate. So that's called the integrating factor. So let's try this. We have the derivative plus 4y on x is equal to 3x squared. I need to calculate my integrating factor. So what is the integral of the function in front of y? The function in front of y is 4 on x when we integrate that. So my integrating factor will be e to the power of log x to the 4, e to the log cancels, I get x to the power of 4. So I'm going to multiply everything by x to the power of 4. I now have something that can be integrated quite easily. You might not see it, but what we've basically done is created the product rule. Write down the first, diff the second, plus write down the second, diff the first. That's what we've got there. See, the derivative of x to the power of 4y would be x to the power of 4 times the derivative plus y times 4x cubed. So I can rewrite the left-hand side as the derivative of x to the power of 4y. And that will equal 3x to the power of 6. So we will now integrate both sides with respect to x. Well, left-hand side, we obviously get x to the power of 4y. The right-hand side, x to the power of 6, we'll add 1 to the power over the power. There is my answer. It looks a bit funny like that, so divide everything by x to the power of 4, I can make y the subject, and there we have it. You'll notice the difference here is when I do have it as y the subject, I don't necessarily get a constant number. In this case, it's a constant divided by x to the power of 4. Verify that this is indeed a first order linear differential equation. So we have to rearrange this and get it into the form that we like. Okay. Well, I can rewrite the right-hand side because x over x is just 1. So I now have it as y over x plus 1. Move the y over x to the left-hand side, and there it is. It's in the form that we like. I've got the derivative minus some function of x times y is equal to some other function of x. In this case, it's a constant number, but that's still a function. And that is a first-order linear differential equation. Let's find the general solution then. Y dx minus y on x is equal to 1. Integrating factor. So I want to integrate minus 1 on x, and that's minus log x. So u is equal to e to the minus log x, so 1 on x. I'm going to multiply everything by 1 on x. So I get 1 on x to y dx minus y on x squared. Again, I've created the product rule, and I end up with this. Now you might not have picked up the pattern, but essentially what you end up differentiating is the integration factor, whatever you worked it out, times y. So once you know the integration factor, you should get straight away what this will come back to. It'll be the integration factor times y. Okay, let's integrate both sides. So I now have y on x is the log of x plus a constant. I'll make y the subject, multiply everything by x. There it is, x log x plus some constant times x. The derivative plus 3y is equal to x. Integration factor, well, 3x. So u is going to equal e to the power of 3x. So multiply everything by e to the 3x. I'm going to differentiate y e to the 3x. Oh, look at the right hand side. I've got to integrate x e to the 3x. Well, I can do that. Sure, I need an extension 2 technique to do it because I'm going to have to integrate by parts, but we can do that. So if I let u equal x, du is dx to v e to the 3x, v is 1/3 e to the 3x, and okay, let's keep going. I now have to integrate e to the 3x. There we go. Divide everything by e to the 3x. I have an answer. So y is x on 3 minus a ninth plus some constant times e to the minus 3x. This is where differential equations can take us. But as I say, we don't have as much fun in this course. Clearly, you won't see ones like that in Extension 1. And in fact, you're not going to see ones in the HSC anyway, that we have to use an integration factor. Let's have a look at an HSC one then. Here's last year's one. Find the particular solution to this. It goes through the point 0, 1 we are told. So x minus 2 to y dx is equal to xy. Separate my variables. Now I'm doing it as a definite integral straight away because it is a particular solution. So when x is 0, we know y is 1. We want to find the relationship between x and y. So on the right hand side, I'm going to have to rewrite that fraction. So I get 1 plus 2 on x minus 2. So we now know the log of y is equal to x plus 2 log x minus 2. Substitute in our values. And now let's rearrange all this. I mean, that is a particular solution, I suppose. It's just a little bit messy. That looks more fun. So log of y is the log of e to the x plus the log of x minus 2 squared over 4. Log of e to the x. Well, let's join those two together. Again, use my log laws. Oh, look, log of y equals log of this. Log equals log. So absolute value of y must equal x minus 2 squared e to the x over 4. So y would equal plus or minus x minus 2 squared e to the x on 4. But we're looking for the particular solution, remember. So which one is it? Is it the plus? Is it the minus? So let's check. And it's the plus. That will work for this one. So x minus 2 squared e to the x over 4. Welcome to the world of differential equations.